That's this week. Yeah. Okay, if you can turn to page 48, I have one last thing that I need to go over with you before we do our begin our test review. This is one of the last sets of integral rules that we have to. I say one of the last few because there's still a couple that are trig related that are involving natural log, and I'll get to that later. This is the more important one here. Now, just a bit of a review from when we did our trig derivatives. Let me review those rules. So the three important ones are arcsine, arctangent, arcsecant, because we know that the ones that are related to them are just the negative versions of arcsine, arctangent, arcsecant. Again, page 48. But I just want to kind of build them out so we can kind of see them. So we know arcsine is arcsine, arctangent, arcsecant. They all have u prime in the numerator. All the denominators are just variations of 1 and u squared. Arctangent is the simplest looking one. It has 1 plus u squared. There's no radical. There's no minus sign. It's just plus signs of everything in within the derivative rule. Arcsecant is the most complicated one. It's got the absolute value of u, square root. The way I remember it is I know the u's are next to each other, so I know it's u squared minus 1 and not 1 minus u squared. And if I can figure out this order, then I can figure out the order of arcsine, which is square root of 1 minus u squared. So that's a bit of a review with derivative arc trig rules. Now, if we're going backwards, the adjustment is that the 1 may not always be a 1. It could be a 1, but it could also be another constant. So if I had a rule that looked like this, integral of du over square root of a squared minus u squared, right? It looks a lot like arcsine. You got the square root. You have a represents the constant, which the a, and the u represents the variable. So constant comes before the variable, and there's a subtraction sign between. And so that ends up giving us arcsine. We have to account for the fact that this a may not be always a 1. So instead of just u, it's u over a plus c. Not exactly the same, but we can see the relationship here. Derivative of arcsine gives us u prime over square root of 1 minus u squared. If I take the antiderivative of this, we're essentially making our way back to arcsine. But if that a constant is not a 1, we have to make sure that it shows up as in the denominator in some form. Likewise, if I want to work from the derivative rule back to arctangent, the integral of du, instead of u prime, we use du. Du is kind of like a way of representing chain rule going backwards over a squared plus u squared. Now, the difference here is that with arctangent, there is a coefficient that's going to be left over. So it's going to be 1 over a arctangent of u over a plus c. They all have u over a, but arcsine is the only one without the 1 over a in front. Arcsecant is the most complicated one. And so if I have du over u square root of u squared minus a squared. So notice how arcsine and arcsecant have a different order. The u's are next to each other. Meanwhile, the order is different between arcsine and arcsecant. So it's 1 over a arcsecant. Now the absolute value is going to show up here, absolute value of u over a plus c. I'm just highlighting the rules that we see here in front of us, right? So let's try example 1 here. Example 1, if we are trying to match this up with one of our inverse trig rules, looks like the best fit is going to be the third one, because we see a variable outside, we see a variable followed by a constant. So the first thing we want to do is, if we want to go through our trig, we want to first set up the form to make sure that we're pulling the correct u and the a value. That's always the first goal of these problems. If you're using arc trig, you have to see if you can get the u and a value to show up for you. So to do that, I'm going to rewrite the problem. And I'm going to force a parentheses squared within my denominator. Okay? Well, just within the radical. So we have to ask ourselves, what can I place inside the parentheses so that this squared will give me x squared? Looks like it's the same thing, right? So I don't have to make any adjustments. It's just going to be x, because x parentheses squared is the same as x squared. But to adjust the 9, what can I put inside the parentheses here? 3. Yeah. So if we go through this exercise, we can ensure that we don't accidentally pull the wrong a and the u value, because the a and u value has to live with an exponent above it. So if we put an exponent above and we make the adjustments, we can make sure that our a value is going to be a 3 instead of a 9, because if we put 9, then it's not quite fitting the rule that we want. Now, our u value, sorry, our a value is 3, therefore our u value is what? X. Okay, so now we're going to go through u substitution, convert everything in terms of u if possible. So u is x, du over dx equals 1, dx equals du. Now our goal is, can we make this look exactly like the rule that we want to apply? I'm going to pull the 5 out in front. Dx is equal to du. X is u, so u square root of u squared minus a squared. After I make those substitutions, it matches perfectly with the rule that I want to apply. So now I'm going to apply my rule. The coefficient is going to be outside of my rule, so I need to include it. So I need to include that 5 times 1 over a. What's my a value? 3, so times 1/3. Arcsecant absolute value of u. So absolute value of x over 3, because that's my a value, plus c. Okay, example 2. 1 over 4 plus x minus 1 squared. If I want to match it up with one of the arc trig rules, which one will be the best fit between these 3? Yeah, because there's no square root, right? That kind of gives it away. No square root. It's going to have to be arc tangent. Okay, so let's go ahead and get our sets of parentheses to show up, because we have to get it into this form so that we can pick out our correct a and u value. What can I put inside the first set of parentheses without changing the overall value of my original problem? 2. Okay, any adjustment needed here? Still going to be what? X minus 1. So whatever's inside the parentheses is your a and u value. Sometimes students ask, wait, how do I know which one's the a, which one's the u value? Your a value will just be the constant. Your u value has the variable in it. Okay, so your u value is the variable expression. So my a is 2. My u is x minus 1. Go ahead and go through u substitution. Let's get everything in terms of u and du to convince ourselves that we have a perfect match with the rule that we want to use. So dx gets replaced with du, because a squared plus u squared, perfect fit. There's my rule to match. There's no leftover coefficient outside of my rule, so I can jump directly into my rule now. So 1 over a, as I follow the rule, I'm going to replace them back in terms of my original variable. So 1 over what? 1 over 2. Arc tangent of u over a plus c. Yes. No, yeah, there's no rules for these. So if we're looking at the inverse trig side of things, we're only going to be dealing with these here. We don't have to worry about this. This is only going to show up on the derivative side of things. Okay. All right. Any questions so far? I think one big thing that students experience is they look at this problem and they say, okay, great. If you're telling me that it's arc trig, then I can match it up. But how would I know it's arc trig and not use substitution problem, right? That's something that that we can experience where we're looking at this going, okay, what if we had no indication that this is arc trig? How would we know that it's arc trig? So here's the way that you can tell. You compare between the degrees of the numerator and denominator. Normally, we see that we can go through use substitution when we see that the degree is staggered by 1, right? You got x squared on one side, x being on the other side. That's usually a good indication that maybe use substitution can work, because if I take the derivative of the higher variable, then it will match up with the lower variable when I try to cancel out. But notice that when you have this situation here, what's the degree of the numerator? Lower than that.
No, 0.
0. What's the highest degree that you see? Ignoring the square root. That's what, degree 2, right? So there's a gap. So anytime you see a gap of 2 or more, that's an indication that arc trig is going to help bridge that gap. So again, we're kind of ignoring that square root as of now. You see that, but overall, this is degree 0 versus degree 2. To bridge that gap, it's hard to do with use substitution. Arc trig is going to do that better for us. Meanwhile, if you look at example 2 here, degree 0 versus degree 2, there's that gap with the denominator being the higher degree. And that's usually indication that arc trig will be the better fit for this problem. Now, when everything is nicely organized in parentheses, we can quickly identify the U and A value, but sometimes the problem is not quite separated as nicely as we would like. And if something is in the form of a trinomial, we want to be able to to get it into this proper form so we can pick out the A and the U value appropriately. So let me show you what that looks like. We'll probably just do example 3 here. Use complete the square to rewrite the integrand. So here we have integral of 1 over x squared plus 6x plus 10. How do we know that this is arc trig? Because there's degree 2, degree 0, above degree 2 in the denominator, degree 2. There's a gap with a higher degree being in the denominator. And this is not an easy way for us to identify our u squared and a squared. So we're going to complete the square so we can get this into a better form, like what we saw with example 2. So we can clearly see something a squared and u squared completely separated from each other. So we're going to play around with this, our x squared plus 6x plus 10. And after we get done with this, we'll be able to get something that is in a proper form. So we're going to complete the square to allow for the x's and the constant to kind of separate from each other a little better. So we'll say x squared plus 6x plus space plus 10 minus space. So whatever number that we are going to find to allow for this to be a nice, clean trinomial factoring, we're going to instantly subtract that number out so we don't make any overall changes to this actual value. So if I do a plus 1 here, I need to have a minus 1 because I don't want to change the overall value of my expression. Okay, so how do we know what to fill in those spaces? Those spaces will be the same value. It'll be b over 2 squared. And your b value is going to be the coefficient in front of the x. Okay, so 6 over 2 is what? And 3 squared is 9. So you're going to put a 9 here and a 9 next to it. You're going to factor the trinomial. What multiplies to be 9 adds it to be 6. x plus 3, right? So if I clean this up, I get x plus 3 squared plus 1. And now we can cleanly see where our u and a value will look like. Okay? We know this is arctangent because arctangent is going to be the only one without the square root. So now let's try to fit into our rule. Let's get the denominator to show up for us. We have to get our expression into the parentheses so that we can clearly see what our a and u values are. So the x plus 3 squared is not going to change. That's the same thing. Do I need to make any adjustment with the 1? 1 is squared, the same thing as 1, right? So now I can look inside my parentheses for my a value and my u value. Yeah.
Test on Thursday, it's 6.1 to 6.4.
Yeah, the test is going to be on Friday.
For 6.1 to 6.1.
Right. Mm-hmm. Well, 6.1 to 6.5. Yeah. Okay. So we make our substitutions here. Dx is replaced with du. The variable is the u. The constant is the a. Once we do that, this is our way of convincing ourselves that whatever leftover coefficient we can keep track of, as well as the fact that we have a rule that we can follow, which is the second rule. So now we just follow the rule. 1 over a. There's no additional coefficients, so there's nothing that we need to include besides 1 over a. What's our a value? Just 1, right? Okay. Arctangent of u over a. So x plus 3 over 1 plus c. I don't need the ones here. I can drop the ones, but ultimately, this is my antiderivative. Let me just go through a quick summary in terms of, especially when there's an integral and numerator and denominator involved, sometimes it's hard to spot exactly what rule we're supposed to use. So I just, on page 58 or page 57, 58, I purposely chose problems that look very similar. So we can kind of talk about the distinct differences in terms of, how do we approach these integral problems that all look so similar to each other. So this is the key here. So I want to just kind of point out some of these things here. So if I have an integral and there's only one term below, I should not have to do anything with u substitution. This is clear. This is just going to be a clean separate into individual fractions. And once I separate into individual fractions, I have 3 separate problems. And usually it's just going to be power rule or natural log to help me work through each of those terms. So if there's only one term below, I shouldn't be thinking about u substitution. I should be thinking about, can I expand and rely on just separating into individual problems and handling them individually. If I have, let's say this one, 5x over 7x squared minus 4, there's too many terms below. I can't separate into individual fractions. This is a good u substitution problem because if my u value is that x squared, that entire denominator, that's going to handle that 5x, and it's going to cancel out nicely. I'm going to end up with 1 over u du, which works. Third scenario, let's say I have 4x minus 3 over x minus 5. If my degrees are not going to cancel out, or if my degree is higher, we're not going to quite see the situation here, but let's say I had x to the 4th plus x minus 4. all over x plus 2. We can cross out that x squared. That x squared is going to force us to have to go through long division, which we're not going to have to deal with. So in this case, right, in this scenario or in this scenario, we can think in terms of synthetic division. Now you see how there's a gap here, right? X to the fourth and x. This is not going to be our trig, because our trig is going to be the other way around. If the degree is higher in the numerator and there's a gap, then we want to think about our trig. But if the numerator is the same or higher than the denominator, and there's multiple terms, that's usually a good indication that we do want to separate them out, but we're going to use synthetic division to do that.
If the degree is higher in the numerator, does that mean that the trig rules are like always going to work, or is that just a sign that they're probably trig questions?
Are we talking about? Let's see. Say that scenario again.
So if the degree is higher in the numerator,
In the numerator, then that's going to be long division, synthetic division.
oh wait, no, the other way around.
Yes, yeah. If there's a gap and a denominator has a higher degree, and there's a gap of 2 to 0, or in this case, this degree of 4 to 1, there's a gap, right? If there's any sort of a gap, you're going to expect arc trig.
Okay.
Yeah.
And then the other way around is long division.
That's right. Other way around is long division. And then if it's just one off of each other, numerator denominator is only denominator being the higher degree, then that's usually a use substitution problem.
Mhm.
Yeah, so I purposely wanted to kind of talk about these 4 scenarios that look so similar to each other and just talk about those distinct differences, because I think that's the hard part, trying to figure out, okay, how do I know what integral rules to use, especially if there's a numerator and denominator involved. Okay, let's go to our test review. Okay, number 1. What's our, well, let's do this. For 1 through 6, I just want to talk through what the first steps are. I think that's the hardest part. If you can figure out what the first step is, then everything kind of falls into place a little bit better. What's our strategy for number 1? Power rule, right? Expand. There's no use substitution. There's only one term here. So expand and then power rule. Okay. Number 2, what's our strategy there? Use substitution. Okay. We'll get a set of parentheses to show up. What's our U value?
1 minus 3, right?
Yeah. All right. Number 3. What about number 3? Power rule, right? There's nothing that's even if this was all raised to the second power, I would still go through power rule because it's manageable, right? It's not like this where I can't expand and there's no ugly exponent that's making it really, really hard to expand. Yeah, so I was just rely on expansion. Sometimes we see parentheses and our natural go-to is, oh, it's got to be use substitution because there's parentheses. That's not always the case, right? Especially if it's a problem that we don't need use substitution for. Okay, number 4. Good. What's our U value?
3x squared.
Good. And that should handle nicely with a 5x. Okay. Good. Number 5. Also use substitution. What's the U value?
7 minus x.
Yeah, U is 7 minus x, right? But there's an issue. What's the issue that we're going to run into? The x squared is not going to go away, so we got to go through that change of variable. Remember that change of variable? We got to go through another set of substitution to get that x to go away. Okay. All right. Number 6. Substitution. U value being 1 minus 2x squared. What's different here is after you go through your substitution, you want to bring it back in terms of x, and then you can work in the bounds, right? And the bounds is the last thing that you do. Okay, so can we try that? Can we try numbers 1 through 6? We talked through the most difficult step. Can you work through the rest of the problem? Okay, I'll come around and see how you guys do. You guys can also check your progress with page 3. Yeah, I know you guys are still probably still working on the first page. I want to talk about two things before the class ends, and that's on page 2. So I want to highlight second theorem again, review that, and I also want to talk about how to find a definite integral for absolute value functions without having to go through a bunch of calculus steps. So there's a shortcut to this. Rather than go through a piecewise function power rule, we can just draw the graph out. Feels a lot easier to just add up triangles rather than having to add up areas of triangles rather than doing power rule for piecewise function. But first, number 7. This is on page 2. Now this is saying, here's our function. Our function is the definite integral from 2x cubed to root x of 1 minus square root of 1 minus t squared. That's what the function is defined as. The function has the integral in it. It's asking for find f prime. So if I want to find f prime, that means f becomes f prime. If I want to represent the derivative of this, then essentially it's the derivative of an integral, right? So this is an indication, okay, I'm going to be applying second theorem because I see opposing operations on top of one expression. So here's a reminder what second theorem looks like. Second theorem says if I have a derivative of definite integral, my f of t is not going to change much, but the integral and derivative will have some noticeable impact on the final answer. And the upper bound is going to get inserted into the function, and the derivative is going to have an impact on the upper bound, which is inserted into the function, so it's times p prime. So it looks a little bit like chain rule, but it's really the fact that we're taking the antiderivative and we're coming back to the derivative, which is we're back to the original function, but along the way, it's going to pick up some stuff as part of the process that it goes through. Now, the difference here is that there's variables above and below. So really, the second theorem is going to do this. It's going to be impacted by both the upper and the lower bound. So it's going to be f of p of x times p prime minus f of q of x times q prime. Okay, so let's set this up here. Okay, I'm just going to follow whatever the rule says. So it's f of p of x. I'm going to start with the upper bound, plug the square root of x in for t. So I get root 1 minus t, because square root of x squared is still going to be just x. Sorry, 1 minus x. By I replace the x, so the t gets replaced with x. Times p prime. So what's p prime going to be? Yeah, power rule, 1/2 x to the negative 1/2. So that takes care of that first portion, minus okay, f of q of x. Replace my lower bound into the variable of my expression. Times q prime. So this whole mess is my answer. All right, number 9. Let's talk about number 9 here. Okay, absolute value of x plus 2. This is really the same thing as this. You got x plus 2 to the right of negative 2. And then you have negative x plus 2 to the left of negative 2. Right? The graph basically looks like this. There's a part that's a positive slope to the right of negative 2. And there's a slope that is to the left of negative 2 has negative slope. But rather than having to go through a power rule for both and plugging the upper and lower bound and splitting it up, it's easier if we just sketch this out and see that, oh, it's just two triangles that I can just add up the areas of these two triangles and I can get to my area. So the first thing that I would do with this is go ahead and graph what this looks like. Absolute value of x plus 2. This is a graph with a vertex at negative 2. And that is extending in the V shape from that point. Now, we want to basically involve the region from negative 5 to 6. So I'm going to mark off where negative 5 is, 3, 4, 5. The 6, 1, 2, 3, 4, 5, 6. So if I were to block off this region, do you see how I see basically two triangles here? Because I'm looking at just between the graph and the x-axis. So the integral, the depth integral from negative 5 to 6 is just totaling of these two triangles. If I can find the base and the height of each triangle, I can do 1/2 base times height, 1/2 base times height, add these together, and that will represent my depth integral. So how do I find the y values at these points, which will represent the heights of my triangle? I can just plug negative 5 into what? Into the function, right? Anytime I'm looking for y value, I can just insert into the function. If I plug negative 5 in for x, what am I going to get for y? Now, negative 5 plus 2 is negative 3. What's the absolute value of negative 3? Positive 3, right? So the order pair here is negative 5, comma 3. That's the y value. That's the order pair there, right? Okay, how about here? What's going to be how can I find the y value here? X plus 2, which is 8. My order pair is 6, comma 8. So now let's find the dimensions here. This has a width of 3, a height of 3, because that's the y value that has a height of 3. 1/2 base times height. I have dimensions enough to get the area of this first triangle. What's the width of my second triangle here? 8. And the height is also what? 8. So I'm just using geometry to get to my depth interval here. So 1/2 base times height, and then 1/2 base times height. I get 9/2 plus 64/2, which is 73/2. So whenever I see absolute value integral problem, I'm just thinking, okay, can I draw my two triangles? Can I find the dimensions of each triangle? And I'm just adding up my two triangles. Right. So y equals absolute value of x plus 2. So my vertex is always going to be whatever causes my x plus 2 to be 0. So that tells me that my vertex is at -2. And once I know my vertex is, I'm just always drawing my graph in the V shape with that being the vertex. So -2 is here. I'm just extending the graph in both directions here. And then the endpoints, I can plug into the original function to get the y value. If I get the y value, I have the height, and I can count to get the width. And I do 1/2 width times height, 1/2 base times height. Okay, so I just want to make sure that we are good with this. Can we try number 10 and see if this makes sense? Find your vertex, draw your triangle, find your dimensions, and add up the areas of those two triangles. Into the original function. Yep.
Reduce the values by 3, 3.
Yeah, that's right. I'm sorry?
Put decimals.
Yes, if it's an exact value. But if it's like 0.3333 repeating, then I want the fractional value. But this you can represent as fractional. Sorry, as a decimal. Okay, check your calendar. You guys have homework. Finishing up the last remaining AP practice. And we'll continue with our test review tomorrow, Wednesday. Help session tomorrow morning. 7:15. Come get the folks.
I am ready to take my on.
Good job, bro. And so.
Which one? Yeah, five. Certification, okay, yeah.
You want to this morning or?
I'm here all day. What's your favorite? But that's the also.
Constant and open. The worst constant and open. A guy that's the same. What's a guy? Yeah.